All right, hello and welcome. Have you ever stopped to wonder how something is changing, not over an hour or even a second, but in one single, tiny, fleeting instant? Well, today we're going to crack the code on right now. We're about to unlock one of the most powerful ideas in, well, all of science and math. Okay, let's dive right in. Just look at that number, 270.49 miles per hour. That is the absolutely blistering top speed hit back in 2014 by one of the fastest cars on the planet, the Hennessy Venom GT. I mean, what an incredible feat of engineering. So, to put that speed into perspective, this car can go from a complete standstill, 0, to 200 miles an hour in less than 15 seconds. That is just an astonishing rate of change. Now, we could easily figure out its average speed over that time, but that's not the real puzzle here, is it? Yeah, the real question is this. Forget that whole 14-second interval. How fast is that car going at one single exact moment? Let's say the exact instant the stopwatch reads 5.88 seconds. Not the time between second 5 and second 6, but right at 5.88. I mean, how do you even measure speed when time itself stands still? And that right there brings us to the core problem we're going to tackle today. I call it the problem of right now. How in the world do you measure change at one precise instant? It feels impossible, right? But it turns out, calculus gives us the key. Okay, so the most important thing to get straight is the difference between these two ideas. Average velocity, that's pretty straightforward. It's just the total distance you traveled divided by the total time it took. You probably did this a million times in high school physics. But instantaneous velocity, now that's the speed you see on your speedometer the exact moment you glance down. And that's our target. So our investigation has to start here with the formula for average velocity. You see, it's the change in position divided by the change in time. It's a great tool, don't get me wrong, but it's got one huge flaw for what we're trying to do. It needs two different points in time. It needs an interval. Okay, so if our only tool requires an interval, but what we want to measure is a single instant, what do? Well, we kind of cheat. Or maybe it's better to say we get really clever. We're going to use all those averages to sneak up on the real answer. So here's the strategy. We know the math completely breaks if our time interval is 0, right? Because you just can't divide by 0. But what if we make that interval really ridiculously small? We can calculate the average velocity over a millisecond or a microsecond, getting closer and closer and closer to a 0 interval without ever actually hitting 0. Okay, let's see this idea in action. Now, just to keep the numbers nice and clean, this table uses a common math function, but the principle is exactly the same for our car. Just watch what happens. As the time interval on the left gets smaller and smaller, approaching 0 from both the negative and positive side, look at the value on the right. It just closes in, doesn't it? It's converging on one single specific number. It's like it's homing in on the truth. And you know what? This brilliant process of getting infinitely close to something without ever actually touching it, it has a name. It's called a limit. The limit is the tool that lets us peek into the world of the instantaneous. It's the value that all our little averages are pointing towards. Now, this whole idea of a limit is super powerful, but trust me, it gets even cooler when you can actually see it. So let's switch over to a graph and watch how this all builds into a really beautiful geometric picture. Okay, so if you graph an object's position over time, the average velocity between any 2 points is simply the slope of the line that connects them. Geometrically, that line is called a secant line. Think of it as a line that cuts through the curve at 2 spots. Now just imagine grabbing one of those points and sliding it along the curve, getting closer and closer to the other. And as those 2 points on our secant line basically merge into one, the line itself pivots until it's just barely touching, or some people say kissing, the curve at that one single exact point. This new line, we call that the tangent line. And this is a brilliant picture of the instantaneous rate of change. So here's the big aha moment. The numerical answer we found using that limit and the geometric answer we just found by making that tangent line, they are the exact same thing. The slope of that tangent line is the instantaneous velocity. That's it. That's the answer to our whole mystery. All right, we've kind of stalked this idea from a distance. We've approached it with numbers. We've visualized it with geometry. Now, it's time we give this incredible concept its official name. This is it. It's called the derivative. Written out as f prime of a, it is arguably the single most important tool in all of calculus.
It's the instantaneous rate of change of a function, and it's the slope of the tangent line at that very same point. It is the mathematical definition of right now.
And here, you see it all tied together in one beautiful package. The instantaneous velocity, v of a, is the derivative of the position function, s prime of a. It's the limit of that average velocity formula we started with as the time interval shrinks all the way down to 0. This elegant little equation, this is the solution to our whole supercar mystery.
So, there we have it. We solved the problem of the car. But you might be wondering, why does this one idea, the derivative, matter so much? Well, because it's not just about speed. It's about change. Everywhere.
You see, the derivative is this universal tool for understanding the rate of change in business, in biology, physics, economics, seriously, you name it. If something out there is changing, the derivative can tell you precisely how fast it's changing at any given moment in time.
Let's look at a totally practical example. Let's say you've programmed your thermostat to cool the house down overnight. Sure, you can measure the average temperature drop over a few hours. That's easy. But with the derivative, you can ask a much more precise question.
And because you can ask a more precise question, you can get a more precise answer. At the exact instant of midnight, the temperature is dropping at a rate of negative 1.6 degrees Fahrenheit per hour. That's the power of the derivative.
Okay, here's another one. This time from the world of business. A toy company wants to know if they should ramp up production on a hot new gaming system. Now, they're not asking if they're profitable overall. They're asking something much more specific. Will making the very next unit increase their profit?
So by calculating the derivative of their profit function right at the 10,000 unit mark, they find that the rate of change is positive. And what that means is, at that exact point in production, making just one more will actually earn them more money. The derivative just gave them a crystal clear yes. So, as you can see, from the speed of a race car all the way to the profits of a company, the derivative gives us this perfect, tiny snapshot of change at a single instant. It's a truly fundamental tool for understanding a world that is constantly in motion. So the real question is, what mystery of right now will you solve with it?